In this section, we're going to be going over infrared spectroscopy. So this is one of the big three spectroscopy techniques. We've already gone over mass spectrometry. And in this section, we'll kind of define spectroscopy as different than spectrometry, which we usually associate with mass spectrometry. But spectroscopy, it's a number of different techniques. Of course, in this section, we'll be talking about infrared, but any technique that involves photons of some kind, we usually typically call it spectroscopy, quote unquote. And we use photons to investigate the properties of that compound. So there's all kinds of different spectroscopy. One major form of it is going to be nuclear magnetic resonance. That's going to be the subject after we get done with infrared. Infrared now, maybe once upon a time you talked about in Chem 1A ultraviolet and visible spectroscopy. That's using visible photons and ultraviolet to look at electron transitions. Rotational spectroscopy, just another example, but we won't get into that at all. That's kind of a specialist type of spectroscopy. But spectroscopy, we use photons to figure out structural properties of a molecule. Now, mass spectrometry, again, we use a different word. We don't say mass spectroscopy, we say mass spectrometry, because the difference here with mass spectrometry is we don't use photons in any way. We already talked about how it works, doesn't use photons. But infrared spectroscopy definitely uses photons. So in the first part of this this section, we're going to go and do some review of the electromagnetic spectrum, talk about how to calculate wavelength and frequency and that kind of stuff as review. Now, infrared spectroscopy, we use this to primarily discover information about the bonds in a molecule. So the most useful information is we get information about functional groups. And so if I look at an infrared spectrum, I've looked at a bunch before, some of the things that kind of jump out at me, I can see very quickly that a molecule has a carbonyl, it has a hydroxy group, it has a triple bond. There's some really characteristic absorptions in infrared spectroscopy that tells us very quickly that the molecule contains a particular functional group, or even the absence of a particular absorption tells us that the molecule doesn't have that functional group. So really, infrared on its own really can't tell you what the molecule is, but it's just more confirmation of a molecule, what you think it is. So in the end, once we've talked about mass spectrometry, infrared, and NMR, nuclear magnetic resonance, these three techniques are the most common and they're most useful techniques for figuring out structure. So infrared photons are passed through a sample, much like UV-Vis spectroscopy. This sample could be a gas, liquid, or solid. We're not going to work with gases in any way in the laboratory. It's too hard to work with gases, but we will work with organic liquids. We'll work with solids. And what we're going to measure primarily is the percent transmittance of photons as a function of the wavelength that we're currently using. So all the wavelengths that we use in infrared are clearly infrared wavelengths. But we do a scan, typically speaking. So we'll talk about what percent transmittance is, and we'll look at wavelength and frequency and this kind of stuff too as a review. Now, the advantage of infrared spectroscopy is also that it's non-destructive to the sample, so we don't have to consume any of the sample, unlike mass spectrometry, where pretty much once you put a sample into the mass spectrometer, it's gone for good. Infrared spectroscopy is definitely the focus of this section, so we'll probably end up taking about 2 lectures, quote-unquote, worth of stuff to get all the way through this. Now, just really quickly, we've already talked about mass spectrometry, but just to remind you, it's the principal measurement of molecular mass of a compound. So in tandem with infrared and NMR, we can figure out the structure of a compound. Structural information, sometimes we can get this from mass spectrometry, sometimes, but we definitely can't figure out the entire structure with just mass spectrometry alone. I've already mentioned again that it's generally a destructive technique, unlike infrared. Now, after we get done with infrared, we're going to talk about nuclear magnetic resonance. This is another type of spectroscopy. It does involve photons, just sort of in a different way than what we're going to talk about now. But it's the most useful spectroscopy technique in organic chemistry. Of the 3 sections that we'll cover, NMR is going to take us the longest to get through because it's the most important. And this one is really important for figuring out the structure of molecules. So infrared on its own actually really isn't good enough to figure out structure. On the other hand, nuclear magnetic resonance sometimes can be used alone, sometimes can figure out the entire structure. So that's why definitely NMR is the most useful. It has the same basis in theory as magnetic resonance imaging, so MRI. In fact, I'm about to get an MRI pretty soon here. And they don't call it nuclear magnetic resonance in medicine because it kind of scares people when you call it that. So, but there's nothing really nuclear about it in the nuclear fusion or fission sense. We'll spend a great deal of time after we get done with infrared talking about NMR, but for now we're going to look at infrared. All right, so this is a review. I need to do a small review of electromagnetic radiation. So when I say electromagnetic radiation, this includes a bunch of different things. It includes radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. All these things fall under the umbrella of electromagnetic radiation. So what is the difference between, say, something like infrared or ultraviolet? And the difference between these types of electromagnetic radiation is, simply put, it's the wavelength, okay? So here we're looking at a sine wave, which is just sort of an easy analogy for what electromagnetic radiation looks like. So remember, with electromagnetic radiation, we think of both light and visible and infrared. We think of it both as a particle, so the particles we call photons, but also we think of it as a wave. Okay, so here's a sine wave just as an analogy. And the way we define the wavelength is, simply put, we measure the distance between one crest and another crest. Okay, so if we can measure this distance, we define that as lambda. So lambda is the traditional symbol for wavelength. And typically speaking, lambda is usually given in meters. That's the SI unit, although sometimes you see nanometers with visible. And we're going to see centimeters sometimes with infrared. But wavelength, it's pretty simple. You just look from crest to crest. So what is that distance? And the way we distinguish one form of electromagnetic radiation from another is just by that wavelength. Okay. Now, on the very long wavelength end of the scale, radio waves, they're very long. They're sometimes meters long. Infrared is smaller wavelengths, visible still smaller, ultraviolet's really small, X-rays are really, really small, and gamma rays are ridiculously small. So that's how we distinguish between them. Frequency, so this is related to the wavelength, and frequency is kind of the tougher one to sort of imagine. So before I get into frequency, it's worthwhile to mention too, as review, that these waves, they are waves, are not unlike surfers' waves, in that this little nano creature right here is catching a wave. And just like real surfers, if you were to picture a real surfer on a real wave, that surfer is not stationary. Really, if they face the shoreline, they're going to eventually reach the shore because the wave is in motion. And likewise, electromagnetic radiation, these waves are in motion as well. Although these waves travel a lot quicker than real ocean waves, these waves travel at the speed of light, which is approximately 3.0 times 10 to the 8th meters per second. Okay, so that's C. That's the general symbol for the speed of light. It's always this value is approximately 3.0 times 10 to the 8th. And so it really doesn't matter whether we're talking about visible light or infrared or radio waves. All those forms of electromagnetic radiation travel at this speed right here, the speed of light. Okay, so we've got the wavelength, we've got the speed. Now, considering that these waves are in motion, with frequency, what you have to do is you have to kind of plant your little vantage point somewhere down here. And just simply put, you're watching for crests. So I'm calling this a crest right here. That's a high point in the wave, or a peak, whatever you want to call it, a crest. And what you're doing for the frequency is you're counting, as this wave is in motion, you're counting how many crests you see per second. Okay, so it's really, frequency is the number of events per second. In our case, we're going to define the event to be crests going by my vantage point. Okay, so I'm counting them, 1, 2, 3, 4, 5, 6. So how many of those crests do I see per second? And so the units of frequency, and by the way, frequency is symbolized by this little character right here. So frequency is number of crests per second. And so the units, the fancy way of doing the units are inverse seconds, and alternative to inverse seconds, sometimes people would call this hertz. Okay, capital HC, hertz. I'm going to pretty much exclusively call it inverse seconds. I don't like to get into hertz too much, but hertz or inverse seconds, same thing. Doesn't matter which one we use. So inverse seconds. Okay, so number of crests that I see going by my vantage point per second. That's how we traditionally define frequency. Unfortunately, in infrared spectroscopy, there's another People use the word frequency all the time, but they mean a different types of frequency. And this frequency in infrared specifically is inverse centimeters. Okay, so the way you calculate this type of frequency is you take the wavelength, you convert it to centimeters, and then you take the inverse of that. I've always, and I mean always, call this wave numbers instead of frequency. Every time I have to call it frequency, I get confused because I'm always thinking of this one right here. So really, in this section, I'm going to personally call this wave numbers as to not confuse myself and therefore you. But if you see frequency discussed in the textbook, a lot of times you will. Just think that it's the centimeters, it's the inverse centimeters kind versus the hertz kind. Okay, so this is a different one. In fact, it's kind of hard to visualize what this represents. So this is not quite the same as this, right? So we're not watching for the number of crests per second. So what does this one represent? So if we take the inverse here, it represents, well, it's just simply put, it's just convert this as centimeters. It's the inverse of it, okay? The reason why we use this type of value in infrared spectroscopy is we're going to see later that the wave number or the frequency is proportional to the strength of the bond. So the stronger the bond is, the greater the frequency of infrared photon that is absorbed. And so I'm guessing that's why they use it, okay? So wave numbers, frequency, whatever. Okay, so I'm going to pretty much use wave numbers. Now, how do we interconvert all these things? So we've got the wavelength, we've got this type of frequency, we've got a different type of frequency. So the one equation that ties together the wavelength and the frequency is pretty simple. It's pretty straightforward. It says c, the speed of light, equals the wavelength times the frequency. Okay, so as long as you keep the value here in meters, and the value here in inverse seconds, when you multiply these two things together, you end up with meters per second, which is exactly what we want for the speed of light. Okay, so this is the equation. So whenever I'm given the wavelength, I can always calculate the frequency, and whenever I'm given the frequency, I can always calculate the wavelength, and c is the speed of light. It's a constant value, so this never changes. Okay, so you can think of this as an equation that relates these two things together. Now, I've already talked about how you calculate this type of frequency. What you do is you simply convert the wavelength to centimeters and you take the inverse of that. That becomes wave numbers. Okay, so that's it for interconversion. Now, finally, the energy of a photon. This is really important as well. For any wavelength of photon or any frequency of photon, this kind of frequency, we can calculate the energy of a photon by saying energy of a single photon, that's the key thing, single photon, not a mole of photons, equals Planck's constant. That's just a constant. It's called Planck's constant times the frequency. So the frequency in hertz or inverse seconds times Planck's constant gives me kilojoules of energy for one photon. This is equivalent to saying, if I had the wavelength instead, I could say h times c over lambda gives me the same thing. So whether I use this form of the equation or this form just depends on whether I have the wavelength given or the frequency given. But either way, I can calculate the energy of a single photon. All right, so energy of a photon, pretty straightforward, except that here's another complication with this calculation. A lot of the time people report not energy of a single photon, but they report energy of a mole of photons. So whatever you get for the energy of a single photon, if you truly want to convert it to kilojoules per mole, what you end up doing is you take the joule amount here. So energy is initially in joules. And if we want to go to kilojoules per mole, what you end up doing is dividing by 1,000. So there's 1,000 joules in 1 kilojoule. So that takes us from joules to kilojoules. And then what you do is if this is energy per one photon, which it is, using this equation, we can safely say that 6.022 times 10 to the 23rd photons per 1 mole. All right, so that's how we convert energy of a single photon into energy of a mole of photons. So we convert to kilojoules, and then we convert to moles. You may or may not see this. I just wanted to mention this. This is kind of like a little sticky point in Chem 1A when I have to talk about this. But this equation, energy of a single photon, this converts into energy of a mole of photons. Okay, so let's see. I think we've covered all these bullet points. This is review again. You probably saw this a long time ago in Chem 1A. It's been a long time. Now let's do some sample calculations just to make sure that we're on track here. We've remembered how to do these types of calculations. So calculate the frequency of a photon with wavelength 4.80 times 10 to the negative eighth. So we're going to use that equation that I just mentioned. The speed of light times lambda times the frequency is the equation we need here. So what do we have? We have the wavelength, but we don't have the frequency. So really, it's not terribly challenging here. We're just going to plug and chug. So C, the speed of light, I've got this memorized. It's 3.0 times 10 to the eighth meters per second equals the wavelength, which is given, times 10 to the negative eighth. Our unknown in this situation, of course, is the frequency. And we're going to solve for nu. So give me a second or two. I'm going to punch this into the calculator and see what I get. And of course I punched it in the calculator wrong. So one more minute. Okay, so I'm looking at a frequency when I do this of 6.25 times 10 to the 15th. The unit here is inverse seconds, or you can list hertz, it really doesn't matter. Another statement about this equation is that since it relates the wavelength to the frequency, you might have noticed by now too that when the wavelength is really, really small, the frequency is really, really large. So they're inversely proportional. So when one value is really low, the other one's very high, and vice versa. Okay, so the second calculation is calculate the energy of a photon with wavelength, the same wavelength, 4.80 times 10 to the negative eighth. We're going to use the E equation. So energy equals, what did we say before? So we're going to have to use this form of it, hc over lambda. And so plugging in the values, I've got this one memorized, Planck's constant. So 6.2626 times 10 to the negative 34th. The units on Planck's constant are joules times seconds. So this is a value memorized. I would always give this to you if I should happen to put this on exam. C is also constant. It's 3.0 times 10 to the eighth. Maybe you remember this from physics or chemistry. And then divided by lambda. So lambda is already in meters. That's good news. It has to be in meters. Okay, so that's going to give us the energy of a photon, and that should do it for the basic calculation. So let's see what we can do here. So 6. All right, so the energy of a single photon, according to this calculation, with 3 sig figs in mind, (10 to the negative 18th joules. This is also per single photon, keep in mind. So does it make sense that the value 4.14 times 10 to the negative 18th joules per single photon, does it make sense that it's a really, really tiny value? And the answer is yes. We're talking about a single photon. And single photons don't pack that much energy into them. That's why it's traditional. A lot of people will go on to just convert this into kilojoules per mole. So let's go ahead and do that. Even though the question didn't ask us to do that, we're going to take this one step further. So 4.14 times 10 to the negative 18th joules per single photon. Okay, so we're going to do this. We can do this in any order. We'll just do it this way first. So 6.022 times 10 to the 23rd. Of course, this is Avogadro's number, and so this is a conversion factor where 6.022 times 10 to the 23rd of anything, in this case we're talking about photons, equals 1 mole of photons. All right, so there's where we converted to moles, and now we're going to convert joules to kilojoules and see what we get. All right, so with once again we're looking at 3 sig figs, so 2.49 times 10 to the third kilojoules per mole. All right, so a photon with this wavelength, which is a really short wavelength, has this much energy in kilojoules per mole of that same photon. So 1 mole of this type of photon packs that much energy into it. All right, so this is the basics. I mean, this is a little bit of review. Most of this stuff should look fairly familiar from Chem 1A a couple years ago. So I just wanted to remind you of how we do calculations in our convert wavelength frequency, but we're going to move on to infrared in just a second here. Now let's look back at the electromagnetic spectrum. So this spectrum covers everything from radio waves all the way through gamma rays. So radio waves at the bottom here have the longest wavelengths, and we're going to see once we start talking about NMR that actually radio waves have their uses too in spectroscopy. So this is a really complicated technique, but NMR uses radio waves. Microwaves, we don't use these. As far as I know, no organic chemist really uses these extensively. But microwave radiation, when it interacts with matter, tends to cause molecules to rotate, actually. So this is sometimes called rotational spectroscopy, and microwaves are what cause that, okay? Now, what we're interested in here is infrared. So when infrared photons interact with molecules, they tend to cause molecular vibrations. We're going to talk about these vibrations in just a second. So that's what infrared's doing. And very characteristic bonds in molecules absorb very characteristic photons, as we'll see. Now, visible is something we covered already in Chem 1A, but visible spectroscopy, we're talking about photons that cause electron transitions. So we're talking about electrons that, say, travel in a hydrogen atom. They travel from the second shell to the third shell and back and forth. Okay, so electron transitions for visible, but also ultraviolet spectroscopy too causes the same thing. Now, X-rays, now we're starting to talk about high-energy photons, so these tend to cause ionization. That's why you don't want to get too many X-rays in a year, because it starts messing with your DNA, and gamma rays are starting to be real serious, so you don't want to be exposed to gamma rays. So let's see. So we've got the longest wavelengths down here, the radio waves, and the very shortest wavelengths at the top with gamma rays. And notice that the energy starts relatively low for radio waves, which have those long wavelengths. You can prove that to yourself with a calculation, but gamma rays pack a lot of energy into them. Each photon has relatively large amounts of energy, and so that's why also that they do a lot of damage too. Okay, so energy is correlated. Energy is the lowest down here, it's the highest up here. So infrared is kind of somewhat in the middle of this spectrum in terms of energy and wavelength. Now, just a general principle to remember is the shorter, the smaller the wavelength. Oops, let me back up here. I keep doing that. Shorter, the smaller the wavelength in centimeters, the higher the energy of the photon. Wave numbers, as we're going to be talking about in infrared spectroscopy, inverse centimeters, are directly proportional to energy. Okay, so let's move on. Let's talk again about the infrared region specifically. So we just looked at the big picture. Now, the small picture of infrared, these are lower in energy and longer in wavelength compared to visible photons. Okay, so visible photons cause electron transitions. I'll remind you that infrared photons, if they're absorbed by molecules, cause bonds to vibrate in higher energy vibrational states. The wavelengths in the infrared region, typically between 2.5 times 10 to the negative 4 centimeters and 25 times 10 to the negative 4 centimeters too, so somewhere in that range. Now, I'm going to be saying this over and over again. It's confusing, but in infrared spectroscopy, wave numbers are used a lot. So wave numbers are inverse centimeter values. So 1 over the wavelength are used, and the wave number values are directly proportional to bond dissociation energies. Now, for example, the scales on an infrared spectrum typically start at 4,000 in inverse centimeters and end up at 500. 4,000 inverse centimeters is higher in energy compared to 500. Okay, so that's one of the advantages of using wave numbers, is they're proportional to energy. The terms wave number and frequency, and keep this in mind at all times, This is not the Hertz type of frequency. This is the CM-1 type. So I'll remind you again that the textbook uses these terms interchangeably. In fact, unfortunately, I think they only use frequency. I tend to use wave number. So keep that in mind at all times. Wave number and frequency mean the same thing in infrared spectroscopy. Okay, so what do those infrared photons do when they're absorbed by bonds? Remember that chemical bonds in molecules are like little springs and they're vibrating constantly. And we're going to see that there's a complex motion for those springs, but think of them as little springs that are constantly being stretched and compressed, so that spring motion like that. And they're always doing this. So a molecule, even at cold temperatures, is constantly vibrating like this. Now, always vibrating, because of this, molecules have vibrational modes, as we call them. So there's a really quick and easy way to calculate how many total vibrational modes a molecule has. We'll see that in just a bit. But molecules have, the more atoms that a molecule has, the more vibrational modes that it has. Okay, they're little springs, those bonds. Another key statement about these vibrations is the vibrational modes are quantized. Okay, so a long time ago in Chem 1A, we talked about visible spectroscopy and the fact that electron transitions, those gap in energy between inner orbitals and outer orbitals, those gaps in energy are quantized. So only very specific visible photons are able to cause certain electron transitions. Well, the same is true when it comes to molecular vibrations. A bond is vibrating all the time, but if you want the bond to go into a higher energy vibrational mode, you got to supply exactly the right amount of energy to cause it to do that. So this whole world is very strange, the quantum mechanical world. Okay, everything is quantized. Only very discrete energy values can be accepted by the molecule. Okay, so instead of electron transitions in infrared, what we do is, if it's the right kind of photon that's absorbed by a molecule, we cause the bond or the vibrational mode to go from a lower energy vibrational mode to a higher. Okay, that's absorption, if it's the right kind of photon. For a bond to be IR active, there must be a change in the dipole moment for the molecule. So just because a molecule has multiple atoms doesn't necessarily mean that all of those vibrations are going to be IR active. So one key thing, got to be a change in the dipole moment. For example, carbon dioxide, is a strange beast. It definitely absorbs in the infrared spectrum. In fact, that's one of the causes or one of the problems associated with global warming, greenhouse gases, is that carbon dioxide absorbs radiation. But of its 4 possible vibrational modes, only, I think it's 3 out of 4 are active and one of them is inactive. So there has to be a change in the dipole moment. So just to be a little more specific about carbon dioxide, if you look at the structure of this, the Lewis dot structure, it's a linear molecule. And the one type of vibration that's possible is called symmetric stretching, where this bond and this bond both simultaneously stretch with equal proportion, but that has no change in the dipole moment, so therefore we say that, that's inactive in infrared. We're not going to worry too much about inactive stuff beyond what I just mentioned here, but it is a possibility that some of these vibrational modes are inactive because there's no change in the dipole moment. All right, so let's look at water as just a good starting case. So water has 3 atoms, of course, and the quick way to calculate the number of vibrational modes for a nonlinear molecule that excludes carbon dioxide, it doesn't work for carbon dioxide. So water is nonlinear, 3n minus 6, where n is the number of atoms. So in water's case, we predict 3 vibrational modes. I'm going to go ahead and show you these 3 vibrational modes. So this software that I have, I just did a screen recording. It's called Gaussian and allows me to, I suppose, crudely calculate and look at the vibrational modes. Reality is sometimes different than what this software gives, but let's go ahead and take a look. So the first vibrational mode that I just clicked on here has a frequency of 1712.8, and it's called scissoring because it looks like a scissoring motion like this. It looks like you're cutting paper. Second vibrational mode is called symmetric stretching. This is the one that carbon dioxide has, but it's inactive because it has no change with a linear molecule. And the third type for water is called asymmetric stretching because it's kind of seemingly out of phase, but it's still stretching. Okay, so water has 3. We're looking at animations of those 3 vibrational modes. Now, there's more than just 3 vibrational modes possible. It's just that water is a fairly simple molecule. I'm just going to take you through six of the vibrations that are possible, although I've read recently that there's more than that. It's just that the 6 vibrational modes are These 6 that I'm going to go through are the easiest to sort of demonstrate on flat paper or whatever. Okay, so I decided that to take you through these 6 vibrations, I think I used to watch the Brady Bunch as I was a kid, so I was thinking that this would be like a good little fun thing to do to take you through the 6 vibrations. So I've created what I call the Vibrady Bunch. And in this little demonstration, you're going to see 2 main types of vibration. One type is called in-plane. It's called in-plane stretching. That's not this one right here. And another type is called bending. Okay, so right now water is doing stretching. It's one type of stretching. It's called symmetric stretching. And in the third case, it's doing asymmetric stretching. So there's just 2 types of stretching. The other 4 motions that I'll take you through are called bending, and those are sometimes called out-of-plane bending motions. And enjoy this little Vibrady Bunch tutorial I'm going to show you. Okay, so now that we've talked about the vibrational modes for molecules, I hope you enjoyed the Vibrady Bunch demonstration. So just 6 of the motions or vibrational modes that we talked about. Now let's talk about how infrared spectroscopy works. So it's very similar to UV and visible spectroscopy. You load a sample into the chamber, but instead of exposing it to visible photons, we expose it to infrared photons one at a time, starting roughly at, typically speaking, these spectrometers start at 4,000 wave numbers and go through 500 wave numbers. So each wavelength at a time. In fact, that's the way that the older spectrometers worked. It took a long time on the oldest spectrometer. When I first got to Shasta College, it was a traditional spectrometer, and it took forever to collect an infrared spectrum because it was just so slow. So what we're measuring constantly as we change the wavelength from 4,000 to 500 is we're monitoring the percent transmittance of photons that make it to the detector. So let me just sketch this out really quickly. I'll do this again in a second. But we've got something that generates IR photons. And as these come out, these photons, the sample's right here, and we're watching to see how many of these photons make it to this detector over here. Now, on the one hand, if the percent T is 100%, that means that of all the photons that we generate on this side, they all make it through the sample and are detected by the detector, 100% T. On the flip side of that, if it's 0% T, then all of the photons that are being generated here are absorbed by the sample, by the bonds. Okay, so that's the key thing to remember. We measure percent T. Now, IR is just a strange beast because in all other forms of spectroscopy, we don't measure the percent T. We measure the absorbance of photons. But I don't know why, but in infrared, we talk about percent T. Now, sampling wavelengths, wave numbers one at a time. It's older technology, like I mentioned. Newer technology exposes the sample to all wave numbers at the same time, and a very complex mathematical transformation occurs. It's called Fourier transform that creates the spectrum from all the simultaneous wavelengths and emissions that are going on. So these are called FTIR, Fourier transform infrared spectrometers. These are the latest, greatest. In fact, the one we have right now, they don't even sell the old ones anymore. It's a FTIR. It also allows the instrument to be very tiny. It fits on our desktop pretty easily. Okay. All right, so let's take a look at a few more details about infrared spectroscopy. No two molecules have the same exact infrared spectrum, so by the time we've sampled all the wavelengths and measured all the %Ts for a compound, different molecules are going to give rise to different spectra. So that's kind of useful because we can identify a molecule by matching up its observed spectrum to a database of spectra. In fact, that's what the crime lab in town does on a regular basis, is they expose the infrared to known compounds and databases. The only exception to this, of course, is our enantiomers. So if you put in the R form or the S form, you're going to get the exact same spectrum from the spectrometer if you do that. Now, depending on what bonds are present in the molecule, and since vibrational modes are quantized, those two details we discussed before, very specific infrared photons are absorbed by very specific types of bonds, and that's why infrared is useful, is because depending on where we see absorptions or %Ts that approach zero, tells us what type of bond we're dealing with, because, you know, again, characteristic infrared photons are absorbed by characteristic bonds. For example, a couple things that are really easy to figure out are things like carbonyls, C double bond oxygen, super easy to spot. It always gives an absorption at 1700 wave numbers. And things like hydroxyl groups, so alcohols, are very easy to spot. They're very easy to spot. CC triple bonds, easy. We're going to march through all these really common absorptions and talk about each and every in turn. Okay? So let's go over again how you generate an infrared spectrum. This time I'm going to sketch it out as a drawing, and then after this I'm going to do a little skit or a little play for you that I did at my house. Maybe that helps enhance this discussion. But I've already mentioned that at some point you got to have something that generates infrared photons, okay? So this is my little infrared source. I call it infrared source sometimes. And this is going to create photons. Again, in the older technology, we would only generate one type of photon when we first started out. So let's just arbitrarily call this 4,000 photon. 4,000 wave number, frequency, whatever you want to call it. And the sample for us, I mean, in a visible spectrometer, we would put the sample into a cuvette, which is kind of a squarish looking thing. In infrared, we put liquids onto these little salt plates. Salt plates are made out of sodium chloride, literally. They're polished and they're compressed and they're really shiny. Obviously, you can't wash salt plates with water because they'll dissolve. So our organic liquid occupies the space between these two salt plates, and as best as we can, we pass these photons through that sample, and on the other side is a detector. Okay, so the detector is just detecting photons if they make it through. All right, so at all times we're just generating one wavelength at a time, so we're going to start at 4,000 wave numbers. Excuse me, I said wavelength before. It's frequency or wave number. And we're going to pass it through this sample and see if any of these photons are being absorbed. Now, there's not a whole lot that absorbs at 4,000, so I can pretty much assure you that the %T for this is 100% transmittance in this case. That's a pretty good guess for 4,000. Now, as soon as we vary the wavelength, so we're going to do the same thing, we're going to change to a different frequency, say something like 1,700. You know, eventually we'll get to this wave number and pass it through this sample. You know, these photons are going through the sample, and we're measuring to see how many photons make it to the detector on the other side. If our molecule contains a C double bond oxygen, we expect that at this frequency we're going to see a lowered %T. So in other words, it's not going to be 100. We're going to see some absorbance. It's going to go down to, well, this is a really strong absorption, so it could approach 0% pretty easily. So C double bond oxygen, we're talking about aldehydes, ketones, really easy to spot because they have a characteristic absorption at 1,700 wave numbers. But that's the essence of it. We generate infrared photons. We change the wavelength one at a time. We pass it through our sample, and we watch to see how many of those photons are being absorbed by the detector. Now, on the computer, of course, this detector is hooked to a computer, and the spectrum that we generate is wave numbers on the x-axis, and that's in inverse centimeters. Typical scale, it's strange in infrared. It starts at 4,000, ends at 500, so it seems backwards. And then on the Y scale, we're measuring %T like I talked about before. Now 4000 pretty much is going to be 100% T at the top here, and this is 0%. Something like an alcohol very quickly is going to dive down like this. CH bonds show up typically in this region. Triple bonds here. Let's see, C double bond oxygen. C double bond oxygen is very strong absorption. That tends to be at 1700. Double bonds here. And then all this business down on this side, there's a lot of absorptions down here. This is called the fingerprint region. The fingerprint region, we'll say this many times as we go throughout this section, is useful only for identifying a compound. So every unique compound is going to have a unique fingerprint region. Other than that, though, there's really not a whole lot we can figure out from this other side here. The main absorptions that we're interested in on the left side of this graph, so towards 4000. So anywhere between 1500 right about here to 4000, these are the really important absorptions. So I promise you we're going to go through all these characteristic absorptions. We're going to talk about one bond at a time as we talk about what to look for in this. Okay, but this is the essence of generating an IR spectrum. So like I said before, I'm going to show you a quick skit of this. Maybe it helps, maybe it doesn't. But I'm going to use the analogy of visible light to kind of show this same process again. So take a look. Maybe it's helpful, maybe it's not. And then we'll pick it up on the other side, start talking about bonds. All right, this is my best attempt to demonstrate infrared spectroscopy. I've got a camera on this side, I've got a light source on this side. So the light source represents an infrared source. Of course, these are visible photons that we see here, but in a real instrument, it's infrared. Humans can't see infrared fine, but this is the analogy, is this light source. On this side, I've got a normal video camera, and the video camera represents a detector. In the infrared spectrophotometer, the detector is an infrared detector. This is a visible photon detector. Okay, so we've got a light source, we've got a camera that detects, and if there's nothing blocking this light source to this camera, then of course we call that, in infrared, we call that 100% transmittance. So all the photons that are being generated there are detected by this camera. If I put something in the light path and block it, my body, I've got a big body, so I block all these photons, then the 100% goes down to 0%, so none of the photons are making it through, and the light source is blocked. Conversely, the absorbance is total, and none of the photons are making it through. In infrared, for whatever reason, they use %T, so nothing blocking, 100% T, I step in the light, 0% T, no photons. Now, infrared photons in particular interact with chemical bonds, and chemical bonds are like little springs. I've got a model of propane here, and in a real experiment what would happen is you'd have your light source, your detector, and you load your sample into the infrared spectrophotometer, you put it between salt plates, you do ATR, whatever the case may be. Here's a propane molecule, and maybe in this instance I put this propane molecule into the infrared. And really, when I generate the first photon, so it's a very specific infrared photon that I'm generating at this moment, and the detector is watching this the whole time, maybe it's the case that this particular wavelength does nothing, it's not absorbed by the molecule, and I still see 100% T between these two things, okay? So at this particular wavelength, nothing's really happening, I still see 100% T. Now, what happens in a real infrared spectrophotometer is we change the wavelength, and so the analogy is I'm going to remove this this is called a warming filter invisible, and notice that the color kind of changes as soon as I do that, and that's also changing the wavelength of the photons, although white light can be argued that it's all photons, but in infrared we're just changing to a different wave number or frequency or wavelength, whatever you want to call it, it's all infrared. Okay, so all of a sudden in this analogy, that's the right wavelength to cause this, what's normally called scissoring. Okay, so this molecule is doing a little bit of scissoring at this point. Now it absorbs that infrared photon at that wavelength, and now it's really doing scissoring. And we see that as an absorbance. So in other words, now we don't have 100% T because those photons are causing this molecule to go into a higher energy vibrational mode, which is, more violent scissoring at this moment, okay? Now, again, in the real instruments, we're going to sample all the infrared wavelengths, and we're going to generate a spectrum that starts roughly at 4,000 wave numbers. It goes down to 500 wave numbers, and we print the spectrum, and that's about it, okay? So that's really how infrared spectroscopy works. So here's an example of an actual IR spectrum. So this is something I generated with our new FTIR spectrometer that we just got last year. This is of the molecule, oh boy, we should remember how to name this thing. So this is going to be an alcohol, and it's going to be let's see, 1, 2. So 2-methyl but 1-ene 3-ol, I think is the name of this thing. Oh, there it is right there. 2-methyl-3-butene 2-ol is the name of this molecule. And what we did here on the infrared spectrometer, we described this already, but the spectrometer starts at 4,000 wave numbers and marches all the way to 500 wave numbers. And so as we start to trace this out right here, we're looking at percent T of, kind of close to 100% T, so really no absorbance to speak of until we get to this part right here, about 3,700 wave numbers, and it starts to dive down like this. So this is strong absorption or a low percent T, and this is really characteristic of this bond. That's the OH bond right here, and so we'll look at this pattern quite frequently in this class. But OH stretch is what this is called. Then it goes back up. Now, practically all organic molecules have absorptions in this region. This is due to a CH stretch, so this could be due to these CH3 bonds here, CH3 bonds here. Everything pretty much has that. This tiny little peak right here, again, we'll say this again later, but this is a CH stretch when the carbon is attached, or it's part of a double bond. So that little absorption right there is a CH attached to a double bond. Nothing in this region for this molecule, but typically if you see a triple bond on a molecule, it's going to show up in this region. This little nubbin right here that kind of seems inverted is actually due to carbon dioxide. And because carbon dioxide is a strong infrared absorber and it's always in the atmosphere, what we have to always do before we actually run this molecule is we have to do a background scan. And the background scan collects all the data for just the air, and then later, by the time we're running our actual sample, the computer subtracts out the background spectrum. Unfortunately, it was a little bit overzealous in subtracting out CO2, and that's why this looks like an inverted peak like there, is because it subtracted a little too much CO2 from the spectrum. But carbon dioxide typically shows up right here. Moving along, this is nothing of significance, and then this is the fingerprint region down here. So let's just go ahead and label this just so we're clear. This absorption is the OH stretch, so it's specifically this bond right here, the OH bond. This one is CH that's attached to a double bond. So this one is that bond right there. This one, these peaks right here are CH3 bonds, so really not a whole lot to say. Most organic molecules have that one. And then the rest, well, this region right here is just called the fingerprint region. So really nothing. I mean, if we really go looking for stuff, we could probably find it, but generally speaking, we tend to ignore the fingerprint region, okay? But this is typical. This is a typical spectrum, so we're looking for these absorptions, and depending on where this absorption occurs, tells us what type of bond we're dealing with. So here's percent T on the y-axis, wave numbers on the x-axis. Now we're going to march through each type of common bond absorption one at a time and just talk about the gory details of what to look for and what shapes to look for each and every one of these things. So stay tuned.